Okay. I'll start by saying a little bit more about the descriptive set theoretic side. And we're going to talk about mouse pairs and Suslin cardinals. Mouse pairs are the model theory side. The Suslin cardinals are the descriptive set theory side. We looked at these sets kappa and the concept kappa Suslin sets. Those. Okay, and my exclusion properties, those that there exists reals and unions and intersections, not necessarily complements or for all reals. We saw, in fact, they have the either S kappa or its dual as the scale property. Yeah, so kappa is Suslin of kappa is Suslin cardinal. We did S kappa is not in over alpha less than kappa less alpha. Okay, so we class this S kappa to kappa Suslin cardinal. Yeah, so, and we saw what they look like in the projective hierarchy. Let me just look at a general projective like hierarchy. The pattern is pretty much the same, but so these are projective like hierarchies where the scale property is involved. Which are in general the gaps between S classes and point classes, those quantifiers in between them in general. So, and reference here is the Jackson. So if we let kappa the limit of Suslin cardinals, we get a look at the next omega. So let's say delta 0 maybe is union over alpha less than yes alphas. And this is closed under both real quantifiers. And yeah, not necessarily counting unions and intersections.
This is by anyway the range is of the kappa. What is delta kappa or
fixed kappa. Yeah.
Like I'm the index with delta.
Delta.
Delta with the index should be kappa or
if you want to do the index kappa, that's okay.
Okay, but like
it's let's see. It's some initial segment of the wage hierarchy that is closed under these operations and is associated to kappa. In fact, let's see. I think kappa works out to be the soup of the pre-roll orders. I think it's the delta. But hopefully, we can erase this from the record if this will. Yeah, this one's called the delta. This is something close from the passages means it has those properties and its wage order was also the soup of the ways in the pre-roll orders in delta, and that's kappa. Okay, so we have this picture Open zero. Hierarchy. Okay, we different type. Type 1 case is cofinality of kappa is omega. Suslin limit of Suslin cardinals of cofinality omega. And the type 1 case is really just like projected hierarchy. So we have 2-point classes at the bottom, which you can 0, 1, 5, 0, 1, like. Use some metaphorical. This is the collection probably means of delta 0. Short one like that. And this is sort of like sigma 0, 1. Over here we have the collection of chemical intersections. 5, 0, 1. Okay. And then we have the zigzag pattern. So scale property here to I11 like. And so on. And this is just like the circular ones have the scale property. The ones, everything on the left side, which is the ones closed under exists reals, is one of the S kappas. And the kappas are either the pre-well ordering modules here, or their predecessors, which have cofinality. So it's just like okay, so that's called type 2 is okay, these are cofinality of kappa. Yeah, kappa is singular, but in chemical code. Okay, and so then we have delta here. There are 2-point classes, non-self-dual pair, which are more awkward to describe. Just past delta. The side that has the pre-well ordering, which I'm actually here, so it's yeah. This you can actually characterize in. This is the kappa homogeneous Suslin sets. Suppose zero is equal to functions projections of P. T homogeneous. So this additional very nice property of trees, not just all the kappa Suslins, but these particular ones, and this ensures that the class is I11 in a sense. It's closed under for all reals. Sound pretty good, but it's not closed under. So it's less good than you think. Okay, so but anyway, it's the base for it has the scale property. So again, we have Now we go up to exist reals. In 0. That is equal to kappa. 0. Homogeneously kappa Suslin, all of the kappa Suslin is like a sigma 1-2 like class, and so on. Same pattern. The S kappas are going, I put them on the right for some reason here. I put them on the right because I started the skid problem. Okay, anyway. That's how it works out. We still have the pre-roll ordering classes. The pre-roll ordering order is the Suslin cardinal and predecessor of that. Okay, there are two more types, and they're not that. The one that's different is type 4. Type 3 is essentially the same. So this is regular one of the Suslin cardinals, but the class at the bottom is not closed under both. So here we have closure under one, both, but we also have this dramatic thing, kappa being singular. You can have kappa regular and still not have closure under both. And then the patterns like so picture just that this bottom class has better closure. This is an example of this is something called the Queenie point class, which has a natural identity and type recursion. Sets that are recursive in the real quantum. Semi-recursive if you like it self-dual.
What's the real thing? What is the real thing?
Just there's a higher type functional, which if you give it a program for a set of reals, it'll tell you whether or not it's an oracle for whether or not that set of reals that you've just presented by some algorithm in the higher type sense for computing it has a number. So people don't know that so much anymore. Let's see. Here's hyper arithmetic sets, the ones that are recursive in the number quantifier. So hyper projective sets are the ones that are recursive in the go to this point class, which is still below inductive. Strictly below inductive.
You said that this class is not closed under anything else.
In this case, yeah. In this case,
How is it like?
The gamma 0 here is closed under both intersections. And so that makes it somewhat better off than
naively, if you just take like two homogeneous trees and you kind of take the opinion of them and add them as one dummy variable.
Yeah. The intersect gamma 0 is closed under intersection because it's in fact you can build that into for all. It's not closed under unit. union of two homogeneously Suslin sets may not be homogeneously Suslin. Yeah, it's actually has ZF proved that on the kappa homogeneous sets of closed under. As I remember, I don't think that's closed under for all. Kappa homogeneous closed under for all.
I just wanted to ask, so the next guy, the guy that's supposed to be like pi 1, is that guy like again S kappa or
This one here.
yeah, so in the type 3 case. Yeah,
In the type 3 case.
yeah,
So I mean, gamma 0. No, S cap is closed under exist. The one that's closed under for all is not closed under exist. Is that what you're asking?
I'm just asking what's the next guy after, so what's the
So this is the pi 1. This is the one, the side that's closed under for all. Yeah, I should have said, I guess, that one of the two sides is closed under for all. The others closed under exists. But that's just true for the unchemical. So take the side that's closed under for all. That's gamma kappa. Orderly property. This rules and
that's gamma 0 again.
this one. Oh no. Gamma 0 I took to be the one that's closed under for all.
You assume that in that case it's closed under both.
I spoke. Sorry. All right, closed under one, but not closed under for all, but not exist. But that's good. Sorry about that. Yeah. Thank you. Okay. So these are the various forms of non-closure, and then finally we have the and this is gamma 0 closed under both modifiers. And okay, so this is that. First class like this. Okay, so here, picture is well, you can't. There's no projective hierarchy based on gamma 0 because gamma 0, if I take one of the two sides has the pretty well living property. Let me let that be gamma 0 side. So this. Okay. Well, applying real quantifiers goes nowhere. I can go up in the wage hierarchy, and we have to go an extremely long way before I find another scale or Suslin. So this is sort of you're inaccessible from there's gamma 0 here, would be, if I'm on the side with the three lower, and that would be. If mu is the next Suslin cardinal, that's mu would be right up to. That's about. You can characterize it. There's something called envelope of M0 using M0 dual. And it has various useful characterizations. Sort of reflection properties that say in this region we haven't really gotten something dramatically new. You get something dramatically new when you get the max Suslin card. Okay, so this is sometimes called the graph in scales. There always is at least some decent gap if you're in this case. That is, if I take M0 together with its dual class, okay, take sets in there. So I guess maybe I want to take the collection of this joint units of these two. Take differences of these two. Take the Boolean algebra and build a projective hierarchy. Now the real quantifier takes me somewhere, but I don't get scales. I could get scales right at the very end of that projective hierarchy, but at least there's some gap of one projective hierarchy before we get to the scale. Okay, so that's called the gap in scales cases.
In order to have this envelope, you need assumptions, right? That, for example, like there's more structure about. Otherwise, you could be already at.
If this is the last Suslin cardinal, so it's like if we're in LO bar, that would be this one class would be sigma 2. And the envelope is P of R.
Yeah. But
it doesn't have to end.
Yeah, I just meant that you want the envelope, and then you can continue like building a projective hierarchy type thing. If you want to draw the same picture, you kind of need to assume more structure, right?
Let's see, at the end of the envelope, yeah, if I want to look at the next omega Suslin cardinals, first of all, the envelope has to end. When it does end, it's the cofinality omega case again. That is, you can show that the wage ordinal of the envelope is cofinality omega, and so we're back to the type 1. At the end of the envelope, you have a type 1. So this is systematically explaining that since the end.
Two of those should be the same. It might be the same.
Let's see. There's there are various things that are not proved. I've been using here that we're at a limit of Suslin cardinals. So if you have a regular limit of Suslin cardinals, this assertion that the point classes are closed under one of the real quantifiers. Intersection. This is a wage of delta is regular, but you're in the gap in scales, then that used to be an open question whether this is true, but I think Jackson solved that. Yeah, so what other, I'm sure what other questions are. Yeah, things are somewhat special here. It's easier to analyze because you have one system. Okay, so that was a look at the descriptive set.
So the question is, you said before that this gap means in particular that before you get in Suslin, you go through the whole, you go through cooperative curve as well. Where do you start with the curve? Because those things are close to the point,
Yeah,
right?
right. No, you start with Boolean combinations.
Okay,
Take the Boolean algebra generated by these
okay,
sets. That's at the very bottom.
Okay.
And then how you can use that to apply real modifiers. In fact, the sort of the whole theory of the envelope in general cases basically much of it's due to Martin, some Jackson and Wood, the connection within the model. Okay, so let's go back to your model theory. Well, when I pass from there to Suslin. And then there'll be a question of whether we hit all of the Suslin problems. Close to it anyway. In some sense, we do that. Okay. So let's suppose we're given let's pair the okay. So I want to find the Suslin representation. Yeah, optimal in the sense that the Suslin cardinal is minimal. Or yeah, well, mainly for its strategy, which is to set of the reals. And of course, its strategy is actually a subset of HC. So you have to code it as a set of reals. Sigma, which is contained in HC. So after Y. Okay. So what am I going to do? Construct a sort of universal iterate of P sigma. Well, we already have them. That's M infinity of P sigma. Okay. So, and then actually we want a universal tree. That is a tree with such that all trees by sigma can be embedded into it. And if you're embedded into that tree, you're by sigma. So we have a direct line of mice, we want some kind of trees. Okay, and then your Suslin representation will just search for, it'll justify a tree as being by sigma by producing an embedding of that tree into this fixed universal. Okay, so you can do that. That is. It's, back. 1, 3. B 1 B that's good. B that's 5 sigma. B model. Right. Be a little careful with this statement because G has to be uncountable. Infinity is uncountable structure. So sigma acts on countable trees. So I meant that every, the club many elementary submodels of T are by sigma. Okay. In fact, I really want something stronger for the Suslin representation. So these should probably written this. Every nominal we oh the is going to say whenever U is a young tree, and it's a hull of this tree in the sense that it is a tree embedding. Okay, that's not sufficiently general for our process for our situation. So we tree embedding. Phi from U to P. P on U is bicycle. Well, since I didn't fully spell out what tree embedding is, I probably shouldn't explain what weak tree embedding is. So weak tree embedding. And need it. Yeah, so whatever the notion means, any mouse critter U lambda is such that it has something called very strong compensation. Which is a strengthening of strong Hall compensation, i.e., if T on Q lambda, on Q lambda means on Q by lambda. And I from U and the T is a we call the tree lighting. And U. So there's a stronger form of condensation than the one that is an axiom. That stronger form of condensation falls from the axioms. It's important that it not be the axiom. Because the way you can produce mouse pairs only directly gives strong condensation. It doesn't get the very part. It's actually quite a bit of work to get the very part.
By two and very long.
Yeah, in fact, they have a different character in that strong Hall condensation has to do with the condensation properties of the iteration process of the tree structure. Condensation properties of the individual models of the tree are not relevant. It makes sense if the individual models are not fine structural. This one folds in condensation of the individual models, their hierarchies and the fine structure. So built to do that. Okay, so this is a fact. Maybe it's here's a long paper. Wow, this is not large. I don't think you can guess the title. Something to do with full normalization for mouse pairs. Oh, paper. Something. Full normalization. Okay, so anyway, that's this is an important part of proving the theorem. So that's it. That's the theorem. You do have a normal tree from P to infinity. So what's the U is equal to this. Oh. Okay. So that gives us a system representation. We can prove that T is by segmented by embedding it into so sigma is well, a cardinality of this tree, which is the same as the cardinality of M infinity. It's normally iterating itself to M infinity. So it's cardinality. Okay. Right, what I said. The S the less equals sigma that's the highest. The second. So branch will look like on the coordinate T, T, you know, it's, you know, okay, so how good is this as a system representation? Well, it's the smallest possible. This is actually Suslin cardinal. Witnessed by this. Does code sigma not be, or is not alpha Suslin for any this is the Kuhn Martin term. And the Martin term says every alpha Suslin well-founded relation on reals as rank. Hopefully it has some plus. So then you need to calculate. It's an easy calculation. From sigma, you get a well-founded relation of this rank, namely, basically the direct limit system is giving you, you know, look at how points in the direct limit system fit into each other by their embeddings. You try to go down in the ordinals as you go up in the direct limit. That's a well-founded relation. Because an infinity is well-founded. Okay, it's a well-founded relation, and if code sigma were alpha Suslin, that relation Suslin. It's a well-founded relation whose rank is at least this, because you're up in the system converging to this, and down in the ordinals of the direct limit that, so to speak, can last as long as the height of the direct limit. Okay, so we have a Suslin cardinal. The cardinality of M infinity. And we've calculated just how Suslin these strategies are. Almost, let's see. Maybe there's a better characterization to this. Oh shoot! I forgot to say there's a point I have skipped over here. Basically, in saying that this is Suslin representation for sigma, I'm assuming that every countable tree by sigma can be embedded into the C. I said that. So that may not be true. Because not all countable trees are used in forming M infinity. It's the trees that are used in forming M infinity that can be embedded into this universal tree that goes down. Okay, so I mean, the trivial example is P is L omega 1 is sharp. That's a muscle. Let's see, I don't want to make M infinity. P is some sharp closure. Excellent. Maybe I just if every X is counted. Okay, then only have it this one. Okay, so P. Thing is, you can't iterate P without dropping. So what's M infinity at P sigma? That's the Breckman of all the non-dropping iterates. Like P. Okay. And the strategy for P is not omega Suslin, because it involves iterating zero sharp, which is way complicated than more than the sigma one. So the thing is, you can have the iteration strategy for P can be complicated because it's because of iterations that have dropped, and they don't contribute to an infinity. So you're not going to get information about this. Okay, so I should say the relevant part. Okay, I don't want to explain what that is. It's beyond what I've just said. Basically, this is the trees which have the property that you can extend them to a tree which is not dropped. Okay, those all contribute to the direct. It's not dropped along the main branch. So the trees that you can extend in such a way that you haven't dropped along the main branch. Okay, then those are sort of all part of this direct limit system, and they can be justified by this tree. The extended plus sun, where S doesn't, or the last branch. No, that's not. So that's the part that's this is
Just a particular remark, or in general, sigma B will complete?
yeah, it can be. At least in this example, actually, code signal was was delta 1. Sigma relevance, especially the empty stuff. So yeah, we can. It's not. Mostly, we don't have to worry about that when we go into situations.
How far in complexity can sigma be? Oh, right.
Yeah. They don't come up with, probably not going to get to this, but given any point class delta, you can look at the mouse minimal error in sigma, which such that sigma is. That's one definition of something called point class. Say that this anyway, you can look at these type of things, and then they're in, deltas are reasonably close point class, sigma relevant. Point class generators. There's no important difference between sigma and sigma relevance. I should say, since we got into it, I should say why is why does sigma relevant the collection that tree that I talked about. So, in other words, why is that tree big enough to project to all of sigma relevant? And then you'll see why I need to be more strict. Well, it's because if I take P, okay, that iterates by our theorem proved that iterates to P sigma of this tree yield P sigma. And I'll take an arbitrary T by sigma. Okay, and then I just extend it to mass. So the final branch of S may not be on the main branch. May not extend the main branch. The doesn't. Okay, well, NVS, because I haven't dropped, this is a point in the direct limit system. So I have an embedding here. That's pi from NVS. I guess I forgot to say in the theorem that this map is the normal iteration map from view of this. Okay. It's not just that UP sigma has the last model, but it reproduces the direct limit. So, okay, so I have a new. B S and its strategy sigma, so yes, it's the tail strategy. And, the point is that the construction here of the proof that P normally iterates actually gives you a way of embedding T. So you equal to normalization of X, not W. W was the normalization was part of the axioms. X is the full normalization of T followed by U followed by V. Of the stack. Unveiling more about why UP sigma exists. Why does UP sigma exist? Because there's a stack of trees from P to sigma, and there's a process called full normalization, which converts your stack into a tree. Okay. And that process has some byproduct. So here we have a stack of 1, 2. The normalization of that infinite stack. Okay, the process produces an embedding, first tree into the shuffled together tree. G process instruction X. Produces embedding. Well, I needed that this thing didn't drop, just to see that it actually reads to this. So that's why what's set for our strategy is Suslin cardinals. Let me just so not all Suslin cardinals are ISIS. There's another one, Suslin cardinals, out of the direct limit system, which is kind of close to it actually. If you remember the examples in the projective hierarchy, there was the wooden cardinals were going to the predecessors of the delta one. Like look at the first one. So Aleph Omega was was the ordinal height of unity of the P was M1 at its wooden couple. One wooden couple. And the strategy. Okay, so that's an example of this phenomenon. The height of M infinity is a system, or literally is a system cardinal, just its cardinality. But there, omega one is equal to the cardinality of something we call beta infinity. This beta. Infinity is strong. Infinity. Kind of off the ordinal set at the wooden, so it's the least strong to the wooden, which is the early height. Okay, so in other words, it's equal to pi from B and one infinity of least strong. what's important about the least strong, it's the first, it's the largest cut. There's no extenders that overlap it. It's a limit of it's actually, okay, and there aren't any cut. It's strong to the top, so in no places. Basically, you can decouple the iterating model above beta from everything below. There's no extenders over that. So there really is a completely distinct iteration strategy. That's too much. Anyway, you can decouple in the sense of the strategy for the thing below. The strategy for the thing below, if we just look at the strategy for M1, this beta, that's really that's weak. But you know, as I iterate M1, I keep moving up this strong cardinal and creating longer initial segments. So that's the thing we want. In beta infinity, so beta infinity takes into account the fact I could use extenders as critical for beta. But you can use the top part. Okay, so it was just to generalize that. But in the P, now P is going to be the analog pipe is going to be this delta one. So it's the soup of delta plus P such that kappa is less than the delta P, and there exists an E on P sequence with kappa and it's total. It's a total, it's total. I can use it to not taking much power of the whole lot. So that's sort of the top of the relevant part. And if you go back to the proof of Suslin representations, in fact, you get the code sigma. You don't have to use all the oracles P. You can just use sort of the part that supports total extenders. So, okay, tau infinity here would be that tau would be delta one. Okay. And then what's on the beta? It's the least thing that's strong to that. So B was even, right? If there is nothing strong to it. For alpha less than alpha P, the ordinal, the order of alpha in P is supposed to be this is the soup of length of extenders. But so nothing is less than tau is strong to it. And has a top block otherwise. Was if so, beta P begins the block, so it's the least alpha. Now the order of the Okay. So. Infinity, the second is. The direct one, I, P second. Infinity. Okay, that's the other system covered on our, let me move script to the top block here, so. Close. I think I need to have an additional hypothesis and cardinal. What's Suslin by this and why? Okay, so this is for the code of the shorts, the part, the relevant short tree part. Witness. Not. You just try to draw a picture for here's P with its top block. Have some tree. A good branch of T. Let's P up here. Okay. Was tau P. The relevant part. There's something called the delta. Delta T is super the lengths of the extenders. The alpha T. So I've been using extenders, which whose lengths are less than this. This is sort of one part of the model. Tree is short if IB. Short if and only if B is short if and only. B is flexible, but it's not short if tau gets me up to delta T. Short tree as you can normally continue because there will be extenders and whose length is greater. So tree short if and only if you can normally probably. Actually, you could only continue with stack. So, the short tree strategy is Is made in infinity Suslin, and what's the representation? There's the 3 U0. And what is it? It's just mu p sigma at some level, restricted to some initial segment. In which initial segment? The part that only we use short trees to generate. That is. So. Critical point of embedding from alpha to the end. We're no longer iterating below with critical points below the image of beta. So the critical point here is greater than I0 alpha sigma. And then the short infinity relevant pi sigma denominator. Just the weak tree embedding. We're now in this smaller tree. It's big infinity, because that's as far as you're moving. And this just says that beta came to rest in at this point. We would shut it up to beta infinity. We're not going to send it further. What the cardinality is of this is maturity, so we get with it's and you can show that it's not alpha Suslin for any alpha less by sort of similar direct line. Martin. Suslin. Those are the 2 sources of Suslin cardinals from outflows. And you get all the Suslin cardinals this way. And yes, if you're below, if you have enough of these mice to take mouse limits, in other words, so this is simply the meat part is what I was talking about. The rest, this next part is sure you proved something.
We'll see.
Try and keep nothing. You start with the proof and then you find the theorem. Okay, so what is the theory? So let's, just look at the mouse here. Well, you know, so again, our context is maybe. But, kappa. The are equal to the orbital of infinity. So I quantitative theorem depends on how many of these pairs we have, you know, which cardinals the direct limit can go beyond. Do a Suslin cardinal. Well, it used to be a cardinal. I should say it this way. Okay, let kappa be less than or equal to volume equivalent. Kappa is a Suslin cardinal. And kappa has this form, which we can just express as saying that kappa is equal to the cardinality of gamma, where gamma is a cut point of the cut points of our mouse with the top plot, which is beta. Wow. Didn't have the top block, and it's a limit. The top tau was a limit. You know, if we really have alpha plus the gamma, the order of alpha and m plus equal to gamma. Form of cut point I need. Seeing how you get the Suslin representations from the mouse limits. So I guess it's still open, and more exhaustive analysis might let you remove cardinality. Maybe the Suslin cardinals are exactly the cut points, not just the cardinalities. But it seems to involve more careful connecting them to one classes. Some questions in classical descriptive set theory that we read, you know, it's in Jackson's handbook paper. It's relating Suslin cardinals to envelopes. Okay. Yeah.
I just wanted to ask you again about the